Hi, everybody, and welcome back to my lab. This is week 11, and we're getting really close to finishing up. Today, we're going to talk about one of my less favorite topics for this course, and it's GD&T. So GD&T is something that you're going to see throughout your career whenever you're dealing with footprints and parts. And so it's important for us to understand what we're looking at. Now, why do I say that it's one of my less favorite things to teach? It's because it's such a massive topic. It's something that really we could spend an entire semester talking about what it means, how to apply it properly, and how to define what is actually said. Okay, so let's get into our slide presentation. GD&T. So the first question is always, what is it? Okay, and in this case, GD&T is a acronym. It stands for geometric dimensioning and tolerancing. It's a way to, as they say here, it's a way for us to say exactly what we mean, and it is in essence a form of communication, much the same as CAD is a way for us to communicate to the people manufacturing or using our parts. GD&T is one of the tools in our toolbox that we can pull out and say, this is how I want to define it. Okay. Now, this is a very old standard. This came out a long time ago, and has been developed over the years, but a lot of stuff hasn't changed. So you're going to see some dates here as we're moving through this, and just ignore them because they still apply. All right. What does ASMY? Okay, so as you can see, this is very, very old standard, 2009, and it has been updated. But the goal of GD&T, as I said, is for communication. There is something you need to understand, however, is that as your tolerances decrease, your cost increases. Okay, and I brought a little sample today of a part that I'm going to use, and there's a backstory to this part and why I wanted to use it in particular. This is actually a bracket for a lawnmower. Many years ago, when I was working in the tool and die industry, we were tasked with building this part, more specifically the tooling for this part. And as is standard with a lot of manufacturing scenarios, we're asked to start building the tool long before the tolerancing is done. And so the way that we built this tool was the easy way, which would be to feed it through the tool this way, and at the end kind of bend this over, and so this gets mounted to the deck of the lawnmower, and the pin for the handle comes in here, and these stops prevent the handle from going too far. And the thought was, when we're designing the tooling for this, is, well, it's a lawnmower part. How critical could any of this be? As it turns out, very critical. The engineer came back and said, look, we want to hold the tolerance from this pinhole to this bottom edge within about 0.1 of a millimeter, which was surprising to us. And so we had quite a conversation around what kind of tolerances were capable with the tool, what kind of tolerances they really needed, and what was really reasonable for the application. And it was quite a heated debate, and we ended up convincing them to use the existing tool. But given their specifications, if we were given that up front, that would have been a very expensive tool to manufacture, because we would have had to do it all basically inverted. So yeah, think about tolerances as you start to apply them. Another great analogy is if I ask you to find me a rock, and I don't care what kind of rock it is, I don't care where it came from, I don't care what size it is, it's going to be a very simple task to just go out in the yard or driveway and pick up a rock. But if I start to give you some very specific specifications, this rock must be quartz, and it must be 3 millimeters by 2 millimeters by 1 millimeter plus or minus nothing. All of a sudden, this is a very expensive rock that you need to actually take and source and manufacture and control. Okay, and so keep this in mind. Okay. So why use GD&T as opposed to other forms? GD&T is a great way for us to clearly communicate what our design intent is. And by clearly specifying the design intent, we actually save money. How do we save money? There's there should not be any remanufacturing required. Everything should fit. There's not going to be any modifications of either the part that's being created or the part that it mates with. And your scrap rate should go down because everybody understands how this part is supposed to work. Right? So before GD&T, there was a lot of confusion. You would see notes like this one, and I'm just going to read it. This entire surface must be located within plus or minus 2 millimeter of its design intent with respect to the surfaces labeled A, the four-way hole labeled B, and the two-way slot labeled C. The entire surface also has a form tolerance refinement equal to 0.5 to itself. This absolutely should sound very ambiguous to somebody without a drawing that goes with it. And you might think that this is some sort of asinine example, but I have actually worked with a gentleman who would make notes like this. In spite of having GD&T available, he would put this long-winded, perverse sort of note that requires some sort of decoding to try to figure out. It's akin to a word problem that you would have got in math back in high school. If a train leaving Baltimore, oh my goodness, right? Why don't you just say what the question is, right? Okay, so here we go. To better explain things, all of a sudden you end up with these massive notes. So the reason why I put this blend here is to make sure that, I don't really care for you going out and making all these notes. As a matter of fact, I worked with one engineer who made a note on a drawing and then he left, but it said, this dimension must not be changed. So the first thing I did when I got the drawing was to change that dimension because, well, I didn't like hearing that. And it was a silly thing, very unprofessional to put on a drawing to say, thou must not change this. Well, okay. And so you can see that this drawing becomes very cluttered as well. Okay. And one other point, what if the person that you're sending this to doesn't speak English? It's very reasonable that you may be sending parts for manufacture in Asia or Europe, or even South America, and there's no guarantee that the people that you're sending it to speak English. So be aware of that. The great thing about math is it is a universal language. Okay, so speaking of languages, this is our alphabet. This is our entire Library of Congress, if you would. Everything that we need to say is basically here. These are very akin to hieroglyphics that you might have seen with the Egyptian sort of language, but they all mean something. And if you have the key, right, you can decode pretty much anything. And so a lot of this will make sense when you just read it. I mean, straightness, obviously, that is a line, and it needs to be straight. Okay, flatness, this is trying to depict, this parallelogram is trying to depict that this is actually a surface and it needs to be flat. Okay, circularity, again, a 2D feature, right? It's round. Okay, cylindricity, now we have a 3D hole, right? It's a cylinder. Profile of a line, so some sort of arc or feature that may not be straight, but we have a tolerance that we want to try to follow. And the profile of a surface, again, this is not going to be a flat surface, but we want to be able to follow the contour. Angularity, obviously, the angle is important. Perpendicularity is the same as angularity, but it is referencing to 90 degrees. Parallelism, that's somewhat self-explanatory. As far as location, now this gets a little bit funny. So we have position, which is going to give us the absolute position of the center of the hole, versus concentricity, which is going to look at the entire shape of the hole and that it falls within its tolerance. Now, runout is something that is very easy to imagine and very hard to apply. Okay, so circular runout, if I had a cylinder, you can imagine at a single point I measure how round it is, and so it's basically the opposite of circularity, and that's fine. But total runout, now I have to define every point on this cylinder, and it becomes difficult to measure. Okay, and so one of the things that we have to keep in mind with GD&T is how we intend people to measure it. And so sometimes, as was the case with this, how are we going to measure it and control it with the situation we have? And I'll come back to a little bit more of that story later on. So continuing on with the example of GD&T being a language, we now have our words or our alphabet, and we need to have some sort of way to structure our language. Much like sentences, we have a beginning, a middle, and an end to GD&T. So this is called a frame. Okay, and in each frame, the beginning tells us what kind of dimension or tolerance that we're looking at. We have a value, and then we have what it's referring to. Okay, so it's fairly simple, and if you know how to read this, you can just glance at it and you can say the position of this feature must be within 0.13. I'm hoping that's in inches on diameter at maximum material condition to datum A, B when it's at maximum, and C. Okay, so we'll get into what exactly that means here in a second. Okay, so maximum material condition. So this becomes a little bit of a mind trap for people. So what is maximum material condition? For a pin, a maximum material condition is fairly easy. You can imagine it's when it's its biggest. Okay, so an example of this pin here, our maximum material condition of a nominal 11.75 with plus or minus 0.25 would be 12. Okay, and the same down here, we have a dimensional tolerance of 14.95 to 14.9. Our maximum material condition is 14.95. However, when we deal with holes, the same rule applies. So we're looking for the maximum material condition. And in this case, that would be when the hole is the smallest. You can think of weighing the part, okay? And so the smaller the hole, the more your part is going to weigh. And so in this case, the maximum material condition for this 12 millimeter hole, which has a tolerance of plus nothing and minus 0.25, 11.75 is our maximum material condition. To see the pocket down here, again, 15 millimeters plus 0.1 minus nothing, 15 millimeters is the maximum material because it's already as big as we can make it, or as small as we can make it, sorry. All right. Datum function and datum reference frames. Okay, so this is difficult to explain because you need to be a little bit conceptual. So a datum is a theoretical exact point. Okay, so in this case, they called a datum this surface. Okay, they called this surface, and they called this hole. And it assumes that they are perfect. Okay, and that is somewhat problematic because seldom are these surfaces perfect. So we need to think that through a little bit. Whereas a datum feature is the actual feature of the part established as a datum. So that means that these weren't necessarily just datums, but they were indeed datum features. Okay, datum targets. So this becomes even more specific. So my datum is a vertical plane. My datum feature is the actual face, and then the datum target is a specific point on that face. Okay, and that's a great way for us to specify a very exact point, and we're going to circle back to that here in a second when we get to a real world example. Now, a datum feature, I said when we were talking about runout, it becomes a little bit difficult to do, and that's because we actually need a datum feature simulator. Okay, so in that case, the axis that runs through the center of my pen would be the datum, and well, we can't actually measure that, and we can't actually pin our fixture, our part to our fixture. That way, we need to make some assumptions and some simulations. Okay. Now, I had mentioned fixtures. So fixtures are a way for us to hold our part in 3D space. And in order to properly contain your part, we actually have what they call 6 degrees of freedom. And so they are the X, Y, and Z physical coordinates, okay, as well as U, V, and W, which are the rotations around those axes, okay? And this is not an easy concept to get a hold of, but I think we can do a pretty good job of really defining what the heck is required. Okay, so here is the theoretical perfect fixture. So we have 3 planes in space, and they define the Z, the X, and the Y. And if you can imagine taking your part and dropping it in there, it's going to lock in and never move, right? So let's walk through each step of this. And so we have, we're starting out, and we have a nice plane, okay? And we drop in our part, but it can move in the X and the Y plane, but it is fixed in the Z, okay? It also cannot rotate about the X and the Y axes because it's sitting on that plane. But it is able to spin, and it's able to move freely along the X and Y. The next thing is that we put in a second plane. And this locks in a lot of the movement. So we basically cut the movement in half. We can no longer move up and down in the Z. We can no longer move back and forth in the, we'll call it the Y position. And we can't rotate this part in any of the axes, okay? It's locked in. And by adding the third one, we now pretty much lock it in, with the exception of we could move it in the X and the Y in, well, theoretically in X, Y, and Z in that positive only. Okay, now we're assuming that we have gravity. That's why the Z says that it's fixed, and the I'm assuming that you're able to push it into the corner. Okay. Now here's an example of a drawing that shows us how you would actually fixture that, and so let's take a close look at this, and you'll see that let's start with datum A down here, and so here's our part sitting on the fixture, and you'll notice that there are these three little balls, 1, 2, 3. What those are doing is they're creating a plane. If you recall, when we were talking about 3D alignment, three points makes a plane, right? And so you can imagine if we had 3 points, 1, 2, 3, we're able to locate this part in space. We're still able to move it, but it's going to be on that plane. And why would we want 3 points as opposed to a flat surface? The reason is that there is no guarantee that this is flat. Okay, either through manufacturing, even though it's supposed to be flat, maybe it isn't. But in this case, we would actually find 3 datum planes. Okay, 1, 2, 3, we'll call it. And those will be control points, okay, that are used to locate this across our A plane. B plane is refined by these 2 rollers. Okay, so again, 2 points. 2 points in this case makes a beautiful line, right? And so again, we're using rollers because the contact point of a circle on a line is basically 0. So by having 2 points, we're able to take away a lot of deviation of this surface. Okay, so if this was some rough or bowed surface, we don't really care because we're locating it. And in this case, we would want to pick those mounting points as our controls because that's where it's going to be held in our on our lawnmower in this case. Okay, and the third one refers to a single point. Okay, so we've got a plane, we've got a line, and now we've got a single point. Okay, and that would locate this part, or this part as the case may be, in 3D space, so that we could measure this hole very accurately. Okay. Okay, so I referred here to datums A, B, and C, and you'll notice this little character. These are basically your datum feature symbols. And so the little triangles refer to the face or the feature, and they can be filled or not filled. It's somewhat irrelevant, but these are your datum features, okay? Yeah. Okay, so now the control frame elements. This is where things get interesting. Okay, so here we go. Positional tolerances. Okay, a positional tolerance is this symbol here, and it refers to where this feature is. And now with a hole, a round hole, it's somewhat easy because it's round. Okay, things get a little bit more interesting, and we're not really going to touch too much on it. But when you have features that aren't round, giving tolerances, positional tolerances becomes problematic. Okay, so we tend to not use position at that point, but we use actual geometric tolerancing. Okay, so next is we've got a cylindrical tolerance. So what is a cylindrical tolerance? And this is something you may actually see with parts that need to get mounted together, probably not transistors, but you may see it with switch mounting, okay, where they start to refer to how square the hole is to the surface. And so here's a great example where they give this tolerance, and what they're looking for is how far off off perpendicularity, the hole has been drilled, okay, or in this case stamped. Okay, yep. So they've got datum A being their main feature, datum B again being the surface, and datum C being this line. And when they put in the true position, okay, then they're looking for the worst case scenario of that hole being out of round, so that if you drop in, let's argue it is a switch, that it's still going to be able to sit square. You don't want your switch sitting on some angle. All right. Okay. Bonus tolerances. Bonus tolerances are what I referred to earlier about maximum material condition, and they allow us a little bit extra. So, for example, maybe my tolerance for this hole is quite tight when the hole is at its smallest. Okay, so what I'm trying to say is, if you make this hole bigger, it can have a looser tolerance. Okay, so there's going to be a maximum to that. Obviously, I don't want my switch falling through the hole, but the minimum clearance, let's argue, is 19 millimeters, but the flange on the top of the switch is 22 millimeters. So I have 3 millimeters of land, but I don't want to be able to see the edge of the hole. So I would work it out, and I would say that my tolerance is goes from 19.5 to 20 millimeters in the hole, and then position the hole so that it would line up regardless. Okay. There's a whole thing on calculating that tolerance, and we're absolutely not going to worry about it. But here is basically a chart of how you might go about looking it up. Okay. So perfect. Here we have an example of a fully dimensioned piece of geometry. In this case, so I'm just looking at it here. Let's start talking about this hole here first of all. So it's talking about having a positional tolerance on this hole, which can range from 0.62 to 0.63, and it must be within 0.010, and this is obviously in inches. Now, that tolerance is when it's at maximum material condition, so the hole is at its smallest, and it needs to refer to datum A, okay, datum B, and datum C, okay, where A is the perpendicularity here. So datum A is referring to this surface here, basically, okay. Datum B is the bottom piece here, and datum C is this one here. Now we have a profile here, this angle, this 30-degree angle, and it needs to be, this whole profile needs to be within 0.02. Okay, so that's probably enough on this drawing example. We're already getting far beyond what you're going to need for your test and what you're likely to need for your career in electronics or electromechanical, but it's very important to be able to recognize this. Okay, so let's get into the in-class exercise. Okay, so let's get into a practical example of this. We're actually going to put some tolerancing to a part. And so I want you to go to DC Connect. I want you to download the starter file, and it's called Week 11 GD&T example, and it should look like this. Now, if yours happens to have the dimensions already there, you might want to delete them and start again. But it should be blank, only this part. And so what this is just imagine a stamped piece of steel that that has some holes in it, and this is an important piece of widgetry. And we want to define where these holes are. Okay, and so let's go over to our drawing of a hatch. And one of the things I don't like is the grid on here. You can keep it on if you want, but you notice that when we don't have a model laid out, we can't actually switch between paper space and model space. And so what we're going to do is I'm actually going to put in the command, which is grid, and we want grid and off. Okay, and that will get rid of our annoying grid and a nice clean drawing. Okay, so base from model space. We want to change this to the top view. I want to mess around with that, and we'll change it from a quarter to keep it at half. Okay, perfect. Enter, 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 and there's our tolerancing, our layout. And this is fantastic. So let's go around, and now we're going to throw a few dimensions at this. And so I'm going to make sure that I'm on annotative, and I'm going to dimension things like this radius. I'm going to put in some dimensions like the overall length. And we can see that I'm not going to have enough space already. So this is great because I can show you if everything is fixed properly, it should move the dimensions with it. If you have little yellow exclamation marks around, here I'll throw one in. It's perfect. You should notice that I have the yellow exclamation mark. It's telling me that it's not actually associated. And so what we want to do is if we click on the little yellow jobby, then we can reassociate it. And so in this case, it's asking us to define the first point, which is the center, and the second point, which is the center. And notice that it gets rid of that exclamation mark. Okay, fantastic. We'll throw in a couple more dimensions, say here and here. And remember, I'm making sure not to put dimensions between my drawings wherever possible. Okay, let's get a diameter in here for the hole. We're going to need that later. And of course, we're going to want the thickness of the plate. All right, and so there we go. We have some dimensions laid in. So now that we've created these dimensions, we want to go back and there's some of them that we wanted to set as basic dimensions, and they're highlighted in the sheet if you're following along there. But how to change them? I really don't want to have to go in and redo it. Okay, so if I go into my dimension styles, one of the styles here is the basic dimension, and because maybe I have a whole bunch of them. But one of the things that you can do is we can actually go in and select the ones that we want to change, and then simply select the style that we want. So this is a great way to go in and modify your dimensioning style. Okay, so far so good. We're okay with this. But next we need to actually put in where our datums are. And so what we want to do is we want to create a new multi-leader. Okay. Here we go, multi-leader, and it should be selected to GD&T datums. And in this case, we're going to start by selecting, say, this midpoint here. I don't really need a midpoint. Let's do that again. I'm going to grab that point there. And I'm going to just pull down a little bit. And we can put in here now, capital A. Okay, so there's my datum A. All right. So there's A. B is going to be this side. Okay, so a couple ways that we can do B. We can try to put it onto the leader here, which will give us some grief. Okay, so I could say nearest. Where'd you go? Nearest. And you notice that it does actually select on here, or we can choose a point on this feature. I'm just going to choose a point on that feature because I want to. So there's B, and then of course we want C over here. Okay, so let's do that one more time. Nearest. Call you C. And I don't really like the positioning of it, so I'll just move it over here a little bit. So there's our A, B, and C datum. Now, here we go. What's next? We've got our A, B, and C. Next, we have to create the control frame, okay? And this isn't difficult, but it's definitely hidden, okay? So where we need to find this is here under dimensions. Okay, we're going to do a little pull down. Okay, and it's this little icon over here. All right, so we'll select that, and it opens up our toolbar. And our toolbar, in this case, we want to set it up very specifically. Okay, so the first thing is to choose the symbol. In this case, the symbol is going to be our position. The second thing is that we want to set diameter. Okay, so you notice it toggles diameter. And our diameter in this case is going to be 0.2. And we can set it at maximum material condition. And we're not going to worry about a second tolerance, but we are going to start to set our datums to A, B, and C. And I'll say, okay. And then we can now drop this. And the idea is you want to put it immediately adjacent to the tolerance that it's referring to. So there we go. So here is our one, our whole of 1, and the tolerance is 0.2 on diameter at maximum material condition to datum A, B, and C. All right, so that fairly straightforward. Great example. You don't need to hand this in to me, but know that you are going to be required to do at least one dimension like this in your final test 3, which is going to be in week 14. All right. So on to the homework assignment. Okay, everybody. So because we're getting so close to the end of the year, there's a couple things that we need to cover, and kind of in preparation for your capstone project. And one of the things that I really need you to do is to import a fuse. Now, originally I was going to have you draw this fuse holder, but it's not really that necessary, and I put a fair amount of time into this, but we can use this tool, this piece of geometry, to really drive home one of the tools that you are going to need, which is how to dimension features that aren't on a plane. Now, as we referred to in the previous week, if I have a hole and it's not perpendicular, you can't actually dimension it properly. And so here is another example where I have a hole on a feature that I would like to have a dimension on. And I'm going to show you a couple other little features on how to dimension this and do a layout that is really quite nice. Okay. And so the first thing is I want you to don't just open the file the way I have here. I want you to import it into your standard drawing so that you can get your border and your title block. Okay, but I'm going to just throw mine in super quick because I want to show you how to create a view that will allow you to put in this dimension. And so, of course, we're going to go in, we're going to do our layout from base, okay, projection view. And in this case, I don't want to look at it square on this way. I want to look at the sides. So if this is the front, let's look at the, see the right? No, let's see the left. Perfect. Okay, so I'm going to throw in this one and call it good enough. And so the view that we're really looking for is basically perpendicular to this face here. And so what I'm going to do is I'm going to start by creating myself a new layer. So let's open up our layer properties. Layer. Stop it. Layer. So I'm going to create a new layer here, and I'm going to make it my current one, and I'm going to throw some color at it. Let's see, true colors, color index, that's what I want. We're going to make this one blue, just because. Okay, and I can close that now. Okay, and what I'm going to do is I'm going to start by creating myself a construction line. Okay, and this construction line is on this face. And the reason why I wanted to do this is now I can take this and I can move it over here. And I can also extend it. So here, for example, if I draw a circle, I can extend. Okay, there we go. It's extended out. And what I'm going to do is I'm going to create a section view of this. And the way I'm going to do that is I'm going to pick my nearest here, just because. So nearest and nearest. And I'll press enter. And we'll choose the correct side. Call that good enough. And then I can move this over to this side. I can now erase these construction lines. And I can leave all of this. But now, if I've done it correctly, I can simply put in my views. So here we go. Let's go to annotate, a diameter, that hole. Fantastic. So, this is great. This is awesome. Let's look at a couple other things here real quick. So I'm going to go over to my layout, and I want to draw your attention to edge visibility. I'm going to select this feature, and I'm going to go under Edit View, and we want to change the edge visibility. Okay. In this case, we can actually put in our interference edges and our tangent edges, and we could do foreshadowing. Okay. And you can see that very quickly, this becomes much easier to see that it's a 3D object. We could do the same here. Change our edge visibility. Okay, so here, there. Click, 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 and say OK. And you can see that this is a much better looking drawing just by doing those couple features. The other thing that we can do is to make sure that our view is actually set up to edit view style. We don't want to show the hidden lines. We can show just the visible lines, and it becomes much easier to see. Okay, so your homework today is actually fairly simple. I want you to recreate this, but I do want a title block, and I want the border. All right. Next week is going to be a work week, so there's no actual lecture, but you should be working on your capstone project. Okay. If you have any questions or comments, please feel free to contact me. I am available via email, and I think we're going to set up a virtual classroom for week 13 before our test on week 14. All right. Thanks, and have a great day. Bye now.